Thank you for the introduction. I would just like to start can you hear me and if you can see my presentation?
Yeah.
Okay, perfect. Okay, so I will talk about the, let's say, new method on apportionment of whole carbonaceous aerosols. So I think that the Grisha's presentation was really good introduction in this field. I will make things much, let's say, much I would say less complicated. It's one of the application of how you can use the seven wavelengths of Aethalometer and in combination with the total carbon measurement. So this is still ongoing study. The paper should be out soon, but still I might not have all the answers for your questions yet. In this study, in contrast to what Grisha said, we are assuming max already. So we are assuming MAC of BC, MAC of brown carbon, even MAC of primary or secondary brown carbon. But then we are using different, let's say, validation techniques to validate our results of our, let's say, apportionment algorithm. I would start with a short introduction on carbonaceous aerosols. They are extremely diverse and dominant, let's say, largest and often dominant fraction of fine particulate matter. The impact on public health and climate, and they are composed of black carbon or elemental carbon and organic aerosol, so OA, and then this consists of different molecular structures. So you always have carbon, but then also hydrogen, oxygen, nitrogen, and sulfur. And this organic aerosol fraction is the largest one within the carbonaceous aerosol and the least understood one. Here I have two documents or two guidelines that were issued this year. I think both of them very important. For example, in World Health Organization guidelines, for the first time, we have a guidelines for black carbon measurement. So there it says that each country should have a, let's say, constant black carbon measurement, and they should also do the source apportionment of black carbon, which I think it's true and very important. For example, the second, the IPCC Climate Change 2021, it says that there is still a big uncertainty on the carbonaceous aerosol impact on climate change. But in all the, let's say, developed countries, the concentrations of carbonaceous aerosol are decreasing, except for Western US because of the forest fires. We are also experiencing wild forest fires here in Europe recently. So I think this will be a, let's say, important topic in the near future. So again, to summarize, carbonaceous aerosol is a sum of black carbon and organic aerosol. Looking only at total carbon, at carbon content, the amount of carbon that can be found in carbonaceous aerosol is called total carbon. BC is almost all just carbon, and amount of carbon that can be found in organic aerosol is called organic carbon, OC. So there are different, let's say, apportionment, component apportionment of carbonaceous aerosols. First of all, carbonaceous aerosol can be primary, for example, like black carbon, which is always primary, the product of incomplete combustion of either fossil fuel or biomass burning. The same goes for primary organic aerosol plus some biogenic sources. And you can have secondary organic aerosols. So these are formed via different pathways. You have the, let's say, pool of volatile organic compounds plus some, let's say, for example, OH or NO3, and in that way the aerosols are formed. So you can have primary carbonaceous aerosol and secondary organic aerosols. In how they affect the climate, it is very important to apportion them to the absorbing part and non-absorbing part. So black carbon is a strong absorbent at 880, but also some part of organic aerosol can absorb light, especially at lower wavelength. But you also have a part of non-absorbing organic aerosol, and this can also have an important, let's say, impact on climate, because such aerosol scatter the light and have cooling effect instead of this heating effect of black carbon. So what we developed recently in aerosol is a combination of two instruments. So one is very well known Aethalometer, measuring, let's say, optical absorption at 7 different wavelengths in real time, and in combination with the newly developed Total Carbon. So this measures the total carbon in high time resolution. So let's say every 20 minutes or every half an hour. You can have a real-time apportionment of total carbon into organic carbon and black carbon. So if you assume a constant OA to OC ratio, this can give you the combination of this instrument can give you the whole mass of carbonaceous aerosol. So this is by using this simple equation here. So it's a, let's say, field-ready combination of instrument that will give you real-time data on carbonaceous aerosol, TC and BC. But you can take, or we took this algorithm even further. So instead of just doing the BC to OC apportionment, we also did some steps further. So our CAS apportionment model, so CAS means the Carbonaceous Aerosol Speciation System, combination of Aethalometer and Total Carbon. Firstly, apportions to BC and OC, so OC is TC minus BC. But then using the BC tracer model, which is quite well described in this paper here, it assumes that the black carbon coming from fossil fuel and primary organic carbon have the same sources, so the biogenic sources needs to be neglected, and they have the same pattern. So by using a combination of a good correlation between BC and primary OC, and searching for the worst correlation between primary OC and secondary OC, you can do the apportionment of primary organic carbon and secondary organic carbon. So, and then using this OA to OC constant, you can have the whole picture of, let's say, carbonaceous aerosol in a way of primary and secondary. Then we can also use the well-known Aethalometer model, which apportions black carbon to black carbon coming from fossil fuel and black carbon coming from biomass burning. And if you sum this all together, you get 4 components. And additionally, by using the brown carbon model, so doing also the apportionment of absorption to the one from black carbon and the one from brown carbon. So this is the part of the organic aerosol that absorbs. You can also have 2 optical components. And because I don't have a lot of time, I will do this step even further. And I don't think that I can explain all the details. You can also, or what we did is also put a mass on brown carbon and also do absorption on primary organic aerosol and also primary brown carbon. So at the end, you get 6 components. BC coming from biomass and fossil fuel, secondary brown carbon, so secondary organic aerosol that absorbs, secondary non-absorbing organic aerosol, primary brown carbon, and primary non-absorbing organic aerosol. So we did different campaigns to, let's say, validate different steps in our newly developed algorithm. I will show you one of those campaigns. This is a long-term, I think it was 2-year campaign in Los Angeles Basin. So, of course, this is western part of US. One of the sampling site using this CAS system was in the central LA. This is known as, let's say, source site. And then one is in the river site, which is known as receiver side. What is important here that let's say you have this diurnal wind profile. So in the middle of the day, you have winds coming from the coast in this direction, and because of this mountain ridge, they are diverted here. So that's why part of the aerosols also are detected here at the riverside. So I will start with analysis of TC and BC measurements. So this is 2 years of 1 hour time-based data, which is, let's say, a big advantage in comparison to offline OC-EC filters. For example, in this sampling site, they are done every 6 days. So every 6 days, you have one measurement point per day that tells you how much TC, OC, and BC is present at the site. So using this, let's say, high time resolution method, you can have diurnal profiles, which I think is the really interesting part of measurements. And just by looking these diurnal profiles for both sampling sites, seasonally, you can see that especially summer is different than other seasons, because there is a big TC peaks, which does not follow the BC peak. So let's have this analysis go through, and then we'll see why that happened. First of all, I would just like to start with this validation of our, let's say, simplified TC minus BC method towards the standard OC-EC method. So like I said, at both sides, there are samplers for 24-hour sampling, and then the analysis of OC-EC using improved A protocol is done. And you can see that we have a nice, let's say, correlation and nice slopes between our high time resolution measurements towards their 24-hour measurements. So this is done. And now, skipping many steps, this is the final result of such advanced carbonaceous aerosol apportionment. It's divided into 6 components. So the colors are shown here at the bottom of this slide. And let's say looking at the looking firstly for the central LA sampling site, looking at the black carbon fossil fuel and primary organic aerosol that are non-absorbing, you can see that they have a similar pattern. It's quite not dependent on seasons. The main source is, of course, fossil fuel traffic. And in the morning, there is a traffic peak. That's why the concentrations go up. But during the day, the wind speed increases, the planet boundary layer also increases. That's why the concentrations go down. And even in the evening, especially in the, let's say, summer months and fall and spring as well, the boundary layer stays quite high also during the evening. So although there is a afternoon rush hour, you cannot see it in the concentration of black carbon and primary organic carbon. Then what is interesting here is the secondary formation. Like I said, during the summer, there is a big peak, which is also present in spring and fall for both sides. While it's mostly non-absorbing, but in the winter, there is a peak in the secondaries also in the evening, in the night, and it absorbs a bit. So this is light orange color here. And this can be explained by 2, let's say, major pathways. The first one is, so this midday photooxidation and OH radicals. And this mostly produce non-absorbing secondary organic aerosol. And this is also present throughout the day, but the peak has when, let's say, the sun activity is the highest. And then you have the this, let's say, more winter process of secondary formation, which is connected to the biomass burning. So you can see that biomass burning, so this brown part of black carbon is increased in the winter also for the LA Central. And this produces a VOC, which is a marker for biomass burning, and it's called catechol. And catechol is a VOC which combined with the NO3 radical, and these dark processes, so increased relative humidity, it will form secondary aerosols, secondary brown carbon, so organic aerosols that absorb. So this is this, let's say, light orange color. But you can also have other, let's say, sub-pathways. One is with biogenic VOCs combined with NO3, and this will mostly produce, again, non-absorbing secondary organic aerosol. So, summarized advanced apportionment looks like this. You can apportion the carbonaceous aerosol in real time in 6 components, and you can get different sources, and by that you can also take action for each of these compounds. So I will just stay a bit on the validation part. Firstly, this is a validation of primary organic carbon or secondary organic carbon through different complementary measurements that were done at the sites. For example, O3 is a nice, let's say, marker for OH radicals. And you can see that especially in summertime, the secondary organic aerosol and O3 concentration are very well aligned, while for the CO or NOx, which are primary pollutants, markers for primary pollutants, nicely agrees with the primary organic carbon. Looking also at this yellow line, so these are ultrafine particles. You can see that there are 2 sources. For example, in spring, one is this primary source, combustion from traffic, while in the middle of the day, you can have this secondary formation of organic aerosol or organic ultrafine particles. So this is validation for black carbon from fossil fuel and biomass burning, looking at NOx and levoglucosan, while there is a better correlation of NOx to fossil fuel in comparison to biomass burning, where there is no correlation. And the same goes for levoglucosan, which is marker for biomass burning. So much more nicer correlation to BC from biomass. Again, primary brown carbon, so primary absorbing organic aerosol, is a good marker for biomass burning. And again, you can see for both sides the correlation with levoglucosan of primary organic aerosol, so that absorbs primary brown carbon. It's much more higher than at the secondary organic brown carbon. Of course, they have different sources. This is comparison to the whole PM2.5 mass concentration. You can see that our line of carbonaceous aerosol is always below the PM2.5 line, but you can see again that carbonaceous aerosol in urban environment or suburban environment is the dominant fraction of PM2.5. Of PM2.5. And this is another way. So this is something that we are doing now, is to look at the primary organic carbon or secondary organic carbon versus NOx, CO, BC, and O3 for all seasons and both sites. So this is, for example, for central LA. You can see that looking at the gray dots are the whole organic carbon, and the red, so the colored one, are the primary or secondary. And you can see that the correlation always increased with the marker that is either marker for primary or for the secondary species. It always increases when you use our apportionment of primary or secondary. So this is also a nice proof on let's say, validating our method. One interesting thing that we observed, and that I also mentioned in the beginning of my talk, is these wildfires. That primary brown carbon is a nice marker for wildfires, especially for the seasons where there is no other biomass burning present. And let's say plotting this graph of hours of the day versus the versus the days in different months, you can see that whenever the share of absorption of brown carbon is, for example, more than 50%, so you will see these yellow dots, this can always be connected to some wildfires that were that happened in nearby of our sampling site. So it's a nice marker also for that. So with that, I would like to conclude. There is still many work to do to validate such method. For example, with all this, what we are missing still is how to better validate the secondary species. So we would need some other chemical analysis, some other complementary measurements, ACSM, for example, and this is something we are planning also now, and we will do in our future campaigns. So thank you for your attention.
Thank you, Martin. Here's few questions. First from Grisha.
Okay.
How do you separate the absorbing PA and SAW from non-absorbing PA and SAW? What kind of MAC do you apply? That is his first question, and he also has one more later.
Okay, so for the just a sec. Okay, I hope I understood the question. So we use the same method. So this BC tracer method, which was used in previous papers only for the whole organic carbon, we use it on the absorption part. So we do the, let's say, BC absorption tracer for the absorption of brown carbon and BC and black carbon. And by that, so this is something we do here. So BC tracer for brown carbon. By that, we get similar result than in this part here, than in step here. I hope I answered the question. Did I?
Grisha has one more question.
Okay.
And which fraction specific organic material organic carbon ratio?
No, just where can I see the questions?
You see this question?
In
chat.
Not yet.
In the chat, but my question is, how do you, which OM to OC ratios you take to get from the absorption coefficient with the MAC to, let's say, light absorbing organic carbon, and then convert this into organic matter mass?
Yeah, so we took different OM to OC ratio. So for in the, let's say, scientific literature, there are different OC to OA to OC ratios, either for primary and for secondary, and you also get the MAC values for primary brown carbon and secondary brown carbon. This is a huge assumption with large uncertainties. So we use the constant numbers, which I don't have it right now here, but our approach is let's take these values and then let's try to validate it backwards. So yeah, different values from different studies.
Thank you.
There is one more question from Justin.
I could address the question. So very nice talk, Martin, indeed. And I want to ask you, if catechol is reacting 10 minus 10 cubic centimeter per molecule per second with OH radicals in the atmosphere, do you expect that catechol could be responsible for secondary organic aerosol formation? Or most probably are nitrocatechols or nitrophenols?
Yeah, that's a good question. So what we are observing is that we have our algorithm shows a lot of secondary brown carbon in the winter times. So then we looked at the, let's say, literature, and we found out that catechol is responsible for that. I mean, it could be responsible. This is something we are still investigating, but what you have written is probably also, I mean, it's true. So this is something we are still working on. Yeah, but yeah.
Okay, thank you. Because I will present today in half an hour probably or less, something about the secondary organic formation from photolysis of nitro aromatic compounds. So direct photolysis, which is much quicker process, releasing huge number of particles in the simulated atmosphere.
Okay.
Yeah.
It would be interesting to hear it. I will. Thanks.
Okay.
There is no questions more, and we need to go further.